And the second one?
Is it direct?
Very good. Yes. Absolutely. We use direct differentiation when I'm given the function, and we use implicit when I cannot solve. If I can solve, I can still, use direct. But if I cannot solve, like in this case, I cannot solve for y. So I have to use implicit. Very good. Thank you so much. Thank you. Good. So we are looking now at 3.6 in MyLab Math, number 1 and number 3. So thank you for bringing that to class. I always enjoy helping you with this. Very good. Okay. So we have y equals f of x equals 2x cubed. We are told that x equals 4. We are told that delta x is 0.04. And they are asking us to find 3 things. Number 1, delta y. Number 2, dy. Number 3, or c, dy. For the given x and dx values and delta x values. Okay, perfect. Okay, so let's see how we address that. So if you remember, I did not put it in the recycling bin because I think I'm going to need it a few times. So delta y, it's f of x plus dx minus f of x. All I have to do is just copy that. F of x plus dx minus f of x. And we are asked to evaluate. It was let me check again. They're asking us to evaluate, right? So it says delta y for the given x, and yes. Okay, perfect. So all we have to do is just plug them in. So for part 1, I will continue here. So 4 plus 0.04, this. 4 plus 0.04 is 4.04, and I have 2 multiplied by 4.04 cubed minus 2 times 4 to the third. That's all I need to do. I'm going to share my screen, and I just punch in 2 times 4.04 to power 3 minus 2 times 4 to the third power, which I know is 64, but never mind. So I got 3.878528. So I don't know how many decimal digits they want. How many decimal digits? Round to 4 decimal places. Okay. So 4 means this. So we should enter 3.8785. And that's part 1. Now dy is f prime of x dx. So first we have to find f prime. Can anyone give us f prime for this?
It's 6x squared.
Very good. So then I have 6 times 4 squared. I wanted to write 16, but I want you to see it. Times dx, but this is the same thing. We always know that delta x and dx are the same value, times 0.04. Okay, so I'm sharing my screen. So here it is. We have 6 times 16, which is 4 squared, times 0.04, and we get 3.84. Any questions so far? Any questions?
No.
Is this okay?
Yes.
Okay, so then they want dy for the given x and delta x values. So dy is the same. What? I don't understand what they want. It's the same thing. Oh, no, no, no. Careful. In part 2, they don't want the value. Sorry. Okay, so sorry about that. So let me share. Where is my screen here? So here they don't want us to calculate it. In part C, they want us to calculate it. So in part B, they only want us to write it as 6x squared dx. That's it. That's what they want for part B. For part C or 3, they want us to calculate. So for this, they only want this. And only in part C or the third part, they want the value. Good. So let's continue now with another problem. We wanted to look at problem 3. So, oh, yes. Very good. Okay, let's talk about this one. Square root of 26. Yes. Okay, so let's start from scratch. Please remember the formula. F of x plus a little error is approximately, or change, little change, error, approximation if you want. It's f of x plus f prime of x dx. This is the same thing with this one. So we are interested in the square root of 26. So first of all, I have to identify the following. I need more colors here. Number 1, I need to identify the function. Number 2, I need to find its derivative. Number 3, I need to find x. And number 4, I need to find dx. So let's analyze just this right now. You don't know anything about anything, let's say. What is the function that you think we are looking at? What is the
ratio?
But is it a ratio?
Oh no. Quadrant.
Just read it. Once you read this, you will never fail. Of
Square
course,
root.
it's the square root of x. Of course. Excellent. Which, can anyone differentiate this for us? So I have it here.
X to the power of 1/2.
But differentiate it. We want to differentiate. What is the answer?
Is it 1 over x squared?
Careful.
No, 2 squared.
To the square root of x. So these are formulas that we've been working with. So please have a list of formulas handy at all times. Good. So this is good. This is good. Now, let's look here. What do you think is x? And what do you think is the minor error? Think in terms of the square root, of course. You cannot take that out of the picture. What do you think x could be? And the tiny value dx could be?
25 and 1.
Absolutely. 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 Because we're talking about the square root. So the closest perfect square to 26 is 25. So then the tiny error is this. You could say, what about 49 minus, what is it, 23? No, because this is not tiny. What about 16 plus 10? No, because this is not tiny. 25 and tiny is 26. Perfect, thank you. Good, so our x is 26, our little tiny is 1. That's all we need, and you will tell me how to fill this in. Let's do it.
It is 25, right?
So say the, oh yes, of course. Sorry. So of course this is the square root of 26. So then the square root of 26 will be approximately. What will you fill in? Looking at what we have here, what will you replace f of x by?
One.
So f is here, x is here. What do we replace f of x by?
Square root of x.
But x is here.
25.
But that's a square root.
5.
Exactly, 5. So this, if the function is the square root, in the function I plug in 25. So then the square root of 25 will be 5. So this piece is 5. Awesome. What do I replace dx by?
1.
That's it, done. What do I replace f prime by? Careful, f prime is here and x is here.
Is it going to be 1 over 10?
1 over the square root of 25, which is 5. 1 over 10, indeed. So this is 5 plus 1/10, or 51 over 10. And this is it. This is how we approximate. And you had no idea that you were able to approximate the square root of 26 with a line, with very simple calculations. You don't really have to calculate that, or don't really have to. Yes, this is not exact. So let me show you. They are not identical. There is always going to be a minor error when we use the derivative, right? So the square root of 26 is one thing, and 51 over 10 is 5.1. So they are not exact. They're not identical. But this is, in my opinion, a pretty good estimate of this. So this is the exact, and this is the approximate using the derivative. Very good problems, thank you. Do we have other questions? Anything else you would like to go back to? Do you need help with anything else? Okay, I would like you to give me any function you want. I want to establish something or remind you of something, and then we'll continue with the last section of this chapter. Can anyone give me any function?
5x to the third.
5x to the third plus e to 3x. Perfect. So now I would like you to please remember the difference between two different things. Derivative and differential. They are not the same. They are not the same. Okay. Can anyone give us the derivative? Anyone? Please participate. It's okay if you're wrong. I'll help you. And you will remember. If you make a mistake, normally we remember. So the derivative is f prime. Can anyone give us the derivative of this?
Is the derivative 15x squared plus 3e to the power of 3x?
Brilliant. Thank you very much. Awesome. Well done. Thank you very much. Now, what about the differential? Please do not confuse the two. The differential is dy. This is the derivative. The differential is something else. And please remember the formula is f prime, but times dx. So the differential dy will be all this in parentheses times dx. Do not confuse the two. So it's 15x squared plus 3e to 3x. We need this in the next chapter. Crucial part of the next chapter. So please understand the derivative of this function is this. The differential of this function is dy, which is all this. It's f prime of x, but times dx. Okay, perfect. So let's, any questions again, anything for me, or can I move on to the last section of this chapter? Do you have anything else from my lab math for me? Anything? Did you encounter anything else? Okay, in that case, let's finalize this chapter with 3.9, related rates. So what is this all about? Derivatives that are in a relationship. Some derivatives that are found in a relationship in an equation, in other words. Okay, so here's an example. See how we get to this, and then we look at problems. So let's suppose I have a balloon. It has very little air in it. I stop pumping air in it. And let's say it's in the form of a sphere, like a ball, right? We don't know now because it has very little air in it. But let's just say at some point in time is this, at some point in time is this, at some point in time is this. So I pump air, pump air, pump air, pump air in this balloon. Okay, I see the radius 1. I see radius 2. I see radius 3. I see volume 1. I see volume 2. I see volume 3. I see a surface area 1. I see a surface area 2. I see a surface area 3. So what happens here? Well, in the first stage, these are the dimensions, right? If you want, the radius creates this volume and creates this surface. Small, bigger. So the radius now is bigger than it was. The volume is bigger. The surface area is bigger. The same thing with the radius and the volume and the surface area in the third case. So you see this is motion. In other words, the rate of change of the radius is somehow related to the rate of change of the volume, and also somehow related to the rate of change of the surface area. Here's the formula. So the formula for the volume of a sphere is 4/3 pi r cubed. So this is a function of time, because as much as I mean time passes and I pump in air, so the volume changes. This is also a function of time. How come? Yes, because I pump an air into this balloon, so the radius changes with respect to time. So when we differentiate both sides, v becomes v prime becomes dv over dt. This is a function of time. We bring down 3. 4 pi over 3 times 3 will be 4 pi times r squared times the inner function prime. So we had initially an equation consisting of these variables. But now when we differentiated both sides, we got an equation that consists of derivatives, rates, derivatives that are related through this equation. That's the idea of related rates. It's another application of differentiation. So this is given to us from geometry. But now we know that the volume changes with time, the radius changes with time. So then when I differentiate, I determine dv over dt, and I differentiate r with respect to time, bring down 3, subtract 1 from the power, times the inner function prime, because this is not a variable, but a function of time. And now whatever I need, I'm given this and I determine this, or I'm given this and I determine this. This is the idea of related rates. So now I'm going to open That's all I have to say. We just have to practice. No, this is not what I wanted. And definitely this is not what I wanted either. So I don't know what I'm doing, obviously. You're witness to this, and I don't know what I'm doing. Okay, I'm getting there slowly but surely. We want to look at chapter 3. We want to look at 3.9. We want the multimedia library. We want to find now. I want to click on this. And we want to be on page